The ocean covers more than 70% of our planet. We map continents from space. We track storms in real time. We measure distant galaxies with precision. And yet, there are parts of the ocean that scientists deliberately avoid, not because they are mysterious, not because they are dangerous in the way people imagine, but because in these regions, our instruments stop behaving as expected. Measurements no longer agree, data becomes unreliable, and scientific certainty begins to disappear. This video explains why some parts of the ocean are still avoided, not out of fear, but because science itself reaches a limit. The ocean covers more than 70% of our planet. From space, it looks calm and familiar. Ships cross it every day. Satellites track its surface constantly. Scientists have studied it for centuries. And yet, there are parts of the ocean that researchers approach very carefully. Not because these places are dangerous in the way people imagine. Not because of myths, creatures, or mystery stories, but because in certain regions, science itself begins to struggle. Instruments become unreliable. Measurements stop agreeing. And the data we collect becomes difficult to trust. This is not a story about fear. It is a story about limits. As scientists move deeper into the ocean, the environment changes quickly. Sunlight disappears within the first few hundred meters. Vision becomes useless. From that point onward, researchers must rely on sound, pressure sensors, and remote machines to understand what lies below. The deeper they go, the more those tools are pushed to their limit. The most challenging regions of all are ocean trenches. These trenches form where massive tectonic plates collide, and one plate slowly sinks beneath another. They are narrow, steep, and unstable. They are not just deep, they are constantly changing. This creates a serious scientific problem. To study the deep ocean, scientists primarily use sonar. Sonar works by sending sound through the water and measuring how it returns. But sound does not travel at a constant speed underwater. Its speed changes depending on temperature, salinity, and pressure. In the deep ocean, these factors form layers. As sound passes through them, its path bends. In open, flat regions, these distortions can be corrected. In steep trenches, sound can scatter, reflect, and return from unexpected angles. This is why maps of deep trenches sometimes disagree with each other. One survey may show a certain depth. Another survey may show something slightly different. These differences are not mistakes. They are signs that the environment itself is extremely difficult to measure precisely. When measurements cannot be repeated with confidence, scientists become cautious. Reaching these depths is also a major challenge. Pressure increases rapidly as depth increases. By the time a research vehicle reaches the deepest trenches, it is under thousands of tons of force. Engineers can design machines that survive this pressure, but survival does not guarantee accuracy. At extreme pressure, materials behave differently. Seals compress. Metal structures flex slightly. Electronic sensors can drift out of calibration. These changes are small, but they matter. A sensor that is only slightly off can quietly distort data without showing obvious signs of failure. This uncertainty is dangerous in science. There are real examples that show how difficult deep ocean research can be. In 2014, a deep-sea research vehicle called Nereus was lost during a dive in the Pacific Ocean. The most likely cause was structural failure under extreme pressure. The loss was not dramatic, but it was significant. That vehicle represented years of engineering and one of the few tools capable of reaching such depths. When equipment like this is lost, it does not just end a single mission. It slows research across the entire field. Even when instruments survive, the ocean presents another challenge: sampling. Many deep-sea organisms are adapted to constant pressure. When they are brought to the surface, rapid pressure changes can damage tissues and alter behavior. Chemical samples can also change as pressure decreases. This forces scientists to ask an uncomfortable question. Are they measuring the ocean itself, or are they measuring what their tools did to the ocean? Science depends on repetition. Reliable knowledge comes from measurements that can be confirmed again and again. But deep ocean expeditions are difficult to repeat. They require specialized ships, trained crews, and carefully planned conditions. A single dive can take many hours, and weather or equipment problems can end missions early. As a result, progress in the deepest parts of the ocean is slow. Humans have reached these depths. The first successful descent happened in 1960, and modern submersibles have improved access since then. But access is not the same as understanding. Routine science requires stable environments and repeatable data. The deepest parts of the ocean do not yet offer those conditions. That is why scientists focus much of their research on regions where measurements can be trusted. Not because the trenches are unimportant, but because unreliable data can be more misleading than no data at all. In the end, the deep ocean forces science to be honest. It reveals the limits of measurement. It challenges confidence. And it reminds us that some environments resist easy answers. Scientists do not avoid these places out of fear. They approach them slowly, carefully, and with respect for what is still unknown. Because in some parts of the ocean, the hardest challenge is not going down. It is coming back with knowledge that can be proven.